am the chair of the Science Advisory Group for the UK Geoenergy Observatories. And the SAG, the SAG, has been called ESAG, was instrumental in creating the science plan as Mike described. It was started in autumn of 2015, and several members of the SAG are here. Do you want to wave? Everyone is a SAG member. Yep, so we've got a fair number of people in the room that you can go and ask about the process. I've been asked to outline the science vision for the UK Geoenergy Observatories, talk about the role of the Science Advisory Group and how we've helped to steer what's happening at the sites, and discuss the benefits to the UK and to the science base and to Glasgow. But this is what it's all really about. Many of us in this room, not all of us, are geologists, and we really, really like rocks. And geology is a really interesting science because it's an experiment that's only been run once. We can't do it again. It's taken, over 4 billion years to do this experiment. We can't repeat it again. So we're at a real disadvantage compared to physicists and chemists who can kind of, rerun the experiment, put different amounts of stuff in their beakers and stir it and see what happens. We can't do that. What we can do is travel across the surface of the Earth to where similar things have happened over different parts of geological time and compare them. But we're hampered by a couple of things. One is that we're absolutely tiny. Okay, we may think we're big and important, but the volume of an average person is 10 to the power of 23 less than the volume of the Earth. The deepest we've ever been is 0.002% of the radius of the Earth. And actually, we're just these little ants scurrying over the surface, trying to understand an incredibly complicated four-dimensional thing that changes in space, in 3 dimensions, and in time, on quite short timescales, on human timescales, all the way up to long geological timescales. And we're doing this where in an environment where the data is very difficult to access. So we know more about the topography of Mars than we do about the topography under the oceans on the Earth, because the sea gets in the way. And there's no atmosphere on Mars, there's no trees and dirt and all that annoying stuff that gets in the way of looking at the rocks. So we actually know far more about the topography of planets outside our own than we do about our own planet. It's expensive to dig holes. I was an extremely lucky person. As a PhD student, I mapped a bit of Utah, and then some American guy came along and said, I'd like to drill 5 boreholes through your field area. What do you reckon? It's every structural geologist's best dream, but it costs an awful lot of money to do that. And 5 boreholes through something that's really very complicated, changes in space and changes in time, is not that much. So the data that we can gather is very sparse. It's very limited by what nature has left us, bits of rock sticking up through fields, or what we've done, cutting nice railway cuttings or road cuttings if they're safe to access. And it's very sparse with respect to the length scale of the heterogeneity that we're interested in trying to understand. So this is where the UK Geoenergy Observatories can really step in and help out. So the idea for the UK Geoenergy Observatories is to have an incredibly well characterised volume of rock at length scales that we're interested in. And so the facility essentially is going to be a volume of rock that we know a lot about. And that's then going to be passed over to the community to design a series of experiments on that volume of rock to try and test new theories about how rocks work, to test new technologies about imaging those rocks, and to perturb the system and see how that changes. So we know that human activities impact the subsurface. Our human activities around energy include taking fluids out, like hydrocarbons, putting fluids back in, like CCS, or cold water, if we're looking at CULF. It involves taking material out. I mean, the energy industry relies very heavily on mining, so we take stuff out, like neodymium for the magnets for wind turbines, and that affects the subsurface in profound ways. And every time we do something to the subsurface, we change its mechanics, we change its chemistry, and we change its biology. And the biosphere goes down to at least 3 or 4 kilometres below the Earth's surface. There are bugs there. Most of the time they're asleep, but when something changes, if the salinity changes or the available nutrients for those bugs, they wake up and they start metabolizing and they change the subsurface. So if we inject a fluid into the subsurface, say we inject CCS, or we take mine water out or pour water out of a hot rock, then we'll change the loads on those rocks. That might change the pore structure. It might change the way the faults behave. We're changing the chemistry of those rocks. We might start getting mineral interactions and precipitate new minerals out, clog up the pore space, or dissolve minerals and create new pore space. And we might wake up the bacteria and get them to do exciting things. And these things are all intensely coupled, very, very difficult and exciting and challenging to work on. So UK Geoenergy Observatories at both sites will do two key things. They will provide a volume of rock that is really well characterised in terms of its baseline. So as part of the planning application process, there's a requirement to collect baseline data and understand what's going to be built into and on. But we want to know what this rock looks like before anybody does anything to it. And it's going to be incredibly well characterised. There are going to be arrays of boreholes and surveys, geophysical surveys that Alison's going to talk to you about in more detail in the next presentation. That means we'll really understand that rock well. And this is important because places where we have similar levels of very good high-resolution data sets are quite limited. And some oil fields, the oil industry might go in and shoot millions of pounds worth of 3D seismic surveys. They might drill millions of pounds worth of boreholes. But they're interested in getting the stuff out. They're interested mostly in the reservoir rocks. They will drill and image what they call the overburden, the stuff above the reservoir. But really, if the oil's gone, it went 60-odd million years ago or whenever, and it doesn't really matter. But there's a lot of these new energy industries where that overburden really, really matters. So stopping CO2 coming back up from a CO2 storage site, the overburden matters. Thinking about heat and understanding the heat resource, you've got to understand what's called the duvet rocks, which are the duvets that keep that heat in. And we need to understand their mechanical properties and how they're going to respond to perturbations. So the idea is that the UK Geoenergy Observatory, UK Geo for short, I'm stumbling over the words, will have impacts on industry and on operators, on how best practice is done by those industries that either with current technologies, so the oil and gas industry should benefit, but also new novel technologies. It should have real implications for regulators. You can't regulate what you can't measure. So understanding how we measure the impact of changes in the subsurface is going to allow us to regulate new things as these new technologies and new resources come on. Environmental monitoring of what the impacts are at the surface or at the near subsurface, which is where things will affect people. Stuff that happens at 4 kilometres depth doesn't really affect people much, but stuff that happens in the zones where we get our drinking water from, or if things escape out to the air in terms of air quality, really matter. So UK Geo will look at that link between the subsurface and surface. And it will provide a platform for innovations. So having this incredibly well characterised volume of rock is going to allow people who are developing entirely new types of sensor or entirely new ways of data processing to calibrate those sensors and those new data processing workflows against something that we understand really well. And that calibration is really important for those innovators to be able to get their tools out to market. If you don't believe that this new logging tool that some fantastic SME has invented is actually as good as what's standard on the market, you're not going to use it. You're not going to risk putting it down a borehole that you've just spent £2 million to drill. So the vision is that these two sites will underpin advances in all of these areas. So as Mike said, there are these 3 elements to the UK Geoenergy Observatories. There's the characterisation of the rock and the monitoring of what's there. There's a facility that's going to allow people to conduct experiments, whether it's new technologies or whether it's actually actively perturbing the system and watching what happens, changing pressures, injecting fluids, extracting fluids, and so on. And there'll be a regional network to monitor all of those activities. And they'll probably monitor other stuff as well. You know, the site in Glasgow will be right next to the Clyde. So undoubtedly we'll find out interesting things about what happens to rocks when floods happen, for instance. Or what happens to rocks when everybody in Celtic Park jumps up and down at once. I kid you not, there was a measured earthquake at a Hungarian rock concert, and the band actually encouraged everyone to jump up and down at the same time to see if they could measure it seismically, and they did. As Mike says, the vision is for this to be as open access as possible, and I say as possible. There is some data that you can put up real time. So seismicity data, the BGS have had for years a web page where you can go and watch in real time, you know, the wiggles on a seismometer. There are other data that will require to be processed before they become meaningful, and the BGS have been learning a lot about this with their current monitoring data in the north of England. If something suddenly goes off the chart because a cow trod on the sensor, you need to filter that out, because otherwise you're going to alarm people that you've had a sudden huge methane release. As UK geo projects go forward, there may be a need to have some data embargoed, especially if we have projects that are joint ventures with companies. But the vision is always to make this as open access as soon as possible within the bounds of what's reasonable for the data. Now, a quick bit about the Science Advisory Group. This is 2 quotes from our terms of reference. And the members of the Science Advisory Group are drawn from UK academia, industry, and regulators. And the idea was that the ESAG, the now UK GeoSAG, I suppose, are responsible for giving expert independent advice to NERC and to the BGS as they go forward building these 2 sites. We have a mandate not just to represent our own views, but to actively go out around the community and seek the views of the community, whether that's other academics, industry, or regulators. And that's really has been what's happening. So we started out, we were convened to support the development of the science plan, and it was a time-limited thing, and we were supposed to be finished at the end of that. But at the end of the process of publishing the science plan, NERC and the BGS were very positive about the experience of having a team of people working together to provide challenge to what the ideas that were coming out of the science ideas process that Mike talked about. So they reconvened the Science Advisory Group. It's sort of an open-ended thing. We meet on a fairly regular basis. We have convened some subgroups that look at specific things. So we have a geological characterization subgroup, which really has been meeting with the BGS as they've been characterizing the 2 sites in England and Scotland, and just peer reviewing what they've done, and checking that they've not forgotten things, or that they are taking account of uncertainties and so on. We have an environmental baseline subgroup who have been meeting to, again, provide challenge to the BGS. So when they've set up, or they're looking at setting up the environmental monitoring networks, we have experts on the Science Advisory Group who say, have you considered such and such? And we have a borehole drilling subgroup, which has not yet met, but the idea is that when the drilling actually happens, those of us who've sat on active drill rigs can say, stuff happens. I mean, if you sit on a drill rig, something always happens. You know, the things break, or you get to a place and the depth wasn't where you thought it was, or whatever, and you have to make very quick decisions. So the borehole drilling subgroup is there. They'll be on call when the drilling's happening. If something happens where a decision is a decision is needed to be made that has a difference to the science. So we've had a problem with loss of circulation in the well. We need to put casing in. We weren't planning on putting casing in. What does this mean for the science plan? There'll be the people on the site will be able to phone up the Science Advisory Group and say, can we talk through with you what the implications are for the science plan? I'm not going to go through the science plan in detail. It's published and available on the NERC website. But the main themes that we came up with were imaging this complex heterogeneous rock mass and imaging it as it changes, either as it changes through normal processes or as it changes through human-induced perturbations, either from regional activity or through what we do at those sites from experiments that are funded to use that facility. Multi-phase flow in heterogeneous media. Now, rocks below a certain level in the UK, it's below about 400 metres, are saturated with water. But there's also gases in there, and there are, if you move those water around, the gas might come out of solution, things change. And understanding multi-phase flow in heterogeneous media is a really exciting and interesting challenge. Just talk to the people at Strathclyde that look at the bleeding and blood and movement of platelets through capillaries. It's really, really tough. And you can do dissections on people. You can't do dissections on huge volumes of rock. That's what ESIOS is supposed to be. Sorry, UK Geo. Damn, sorry, Christina. Mechanical response to artificial perturbations, I've already said. Biogeochemical response to artificial perturbations. I got very excited about this when we were doing the science plan. I think that biogeochemistry is one of the really exciting forefront areas of geoscience. Not only understanding what happens naturally when changes happen, but can we engineer those bacteria to do stuff to help us? One of my colleagues at Strathclyde has managed to seal up cracks in granite by encouraging the bacteria to produce calcite. And if you see her cores, you cannot break those things. So we can look at how you engineer things to help us. And then, of course, surface and subsurface interactions. So these sites will have an extensive network of monitoring of the surface, air quality, and so on, and the near subsurface, the bit where we might do stuff that impacts people. So in the interest of time, I'm going to do that annoying thing and flick through those slides, which is all the science plan stuff, and finally talk about what it means for Glasgow. So we will end up with a hub for world-class science and engineering. We will end up with a diamond synchrotron equivalent for geology in the East End of Glasgow. And the East End is a rapidly changing place. It's changed a lot since I last came here, before the Commonwealth Games, but it's still a very deprived area, and having that will bring people in, it will bring activity in, very much in the way that the move of BBC Scotland out of the very wealthy West End across the Clyde has helped to revitalise that area of Glasgow. It will bring in world-leading scientists to Scotland and the UK to use these facilities, and will network our science into global efforts around subsurface research. In Glasgow, it will develop heat infrastructure. So the vision for this site isn't that we're going to just be doing academic stuff, but we will be producing heat. And the team at the BGS are talking to potential local users of that heat. But we will also produce the expertise. So Glasgow's actually been very active in this. Mike said, can we heat homes? I can tell you the answer. The answer is yes. And there are flats in Shettleston, not far from here, the Glasgow Housing Association flats, that have had their gas bills cut by 60% by mine water heat. So we can do it, but there are some really, there are science questions and interesting engineering questions about how do we do that at scale. Strathclyde University is in the middle of putting in a district heating network. Glasgow University's already got one. So Glasgow's really taking the whole idea of district heating very seriously. And finally, there's a really exciting opportunity to involve the local citizens of Glasgow in citizen science and education. So as I left for work a bit early this morning, because I hadn't finished my talk, my daughter said, "What are you doing today, Mum?" And I told her, and she went, "Wow, that's cool." So there are already 2 small citizens of Glasgow who are really excited about getting involved in this site and really looking forward to heat. She was a bit disappointed we weren't going to be plugged into our house, but maybe that will happen if we get a big enough district heating network. So I'll leave it there. Thank you very much.